HP 3D Printing's demo room in our site in Barcelona. Today, I want to talk to you about how additive manufacturing and specifically HP's technology solution in 3D printing can actually benefit the world of robotics and automation. My name is Claudia Galdini. Here on the screen, you can see my contact information. I am a segment manager here at HP 3D Printing, and let me walk you through these topics today. We will start off with the introduction of additive manufacturing. So how it is, what are its advantages? And finally, how can AM be applied to robotics and automation? Specifically, we will also dig deep into HP's technology solution. Then we will make some considerations about designing for additive, and we will talk about what mistakes to avoid. At the end of the presentation, I will introduce you to some of our customer success stories, and I will actually show you some real-world application from the demo room. Also, make sure to submit to us any question, doubt, or curiosity that you might have. We will have a live Q&A session at the end of the presentation where I will try to be as exhaustive as possible. Let's start with today's manufacturing scenario. When we talk about manufacturing, we can basically group various methods into three big families. Subtractive manufacturing, in which material is subtracted, removed, like for example, CNC machining. Formative manufacturing, where there are technologies such as inject molding or extrusion. And finally, additive. In additive manufacturing, which is a topic that we will dig into today, basically what happens is the opposite to the first of these three categories. It basically involves adding material layer by layer. Before starting, it is important to say upfront that additive manufacturing does not want to replace other technologies outright. What we need to do is to think of additive as one of the tools in our toolbox that can actually be powerful and really powerful when used properly to walk along with other manufacturing methods. Additive manufacturing is going to complement the traditional process, and it is going to change the way that we produce. Therefore, we must be aware of the different technologies on the market, and we must become familiar enough with the one we adopt in order to take advantage of its benefits. So I am talking about different technologies. That is because if you choose the right process and you pair it with the right material for your application, that's when you can actually start realizing some of these advantages. For example, you can think of speeding up your design cycles compared to most traditional methods, at least, and accelerate both innovation and time to market with your products. You can also reduce your physical inventory and instead develop a digital inventory, since you can print on demand. This also means that your supply chains will be more robust. Now you can either print directly in-house or rely on a local network of digital manufacturers. We actually saw the power of this in full effect during the pandemic. Supply chains were struggling to keep up with really critical medical equipment. So we saw a lot of companies with printers stepping up and filling in those gaps, printing face shields or respirators, even nasal test swabs. Finally, you'll be able to take more control over your capital expenditures, since you can be more strategic about when you actually need to go to a tool solution, like for example, inject molding or CNC, versus simply leveraging additive manufacturing for bridge production or final production. As I mentioned before, I have been talking about choosing the right technology, and I actually want to reinforce that concept because it is extremely important to choose the best match between what 3D printing can offer and every company's needs. Obviously, from HP, we provide one specific solution. So, for example, if you are mainly looking at just a few prototypes here and there that do not need that much quality finishing or that have a kind of wide margin of error, then maybe a smaller machine like an FDM machine might work better for you. But if you are looking at final parts or components that you will use consistently, if you need high quality and precision, maybe buying an FDM could actually slow you down when you compare yourself to other competitors in the field that are instead investing in different technologies like HP's Multijet Fusion. But how does the spectrum reduce? Objectively, when you choose a technology, there are three main things to be taken into account. Your product's capabilities. So for example, let's say that you need a very large part, like a large jigs and fixture or a large end-of-arm tooling. Not all technologies obviously have that capacity. And so the technology options reduce. Same with very high dimensional accuracy. For example, for a very small needle bearing cage where the margin of error must be minimum. Obviously, not all technologies will be up to the task. Again, materials come into play, as I mentioned before. And the other two things to be taken into account here are material price, and that is pretty self-intuitive, and also material nature. If you produce parts that need to go through some specific regulation tests, for example, or need to work in very high temperatures environment, obviously not all technologies will match the material that you need and will work for you. Anyways, among powder bed technologies, HP's Multijet Fusion stands out. To make an actual comparison, not only with traditional methods like inject molding or CNC, but also with other 3D printing technologies on the market right now, let's have a look at this slide. So first of all, when compared to traditional manufacturing methods, additive manufacturing from HP 3D printing actually allows more customization. You can customize your components in a very economically viable way. New and complex designs and flexibility. Without the limitations of a mold, for example, you can say yes to what you couldn't instead with traditional manufacturing methods, also thanks to all the software providers that there are. And then costs and time savings. You can cut on the molds and tools that might be too expensive to produce, and the turnaround times are reduced as well, since any design change can be done in almost a click, and the new edited batch of parts can be good to go in days or weeks, instead of weeks or months that would take for CNC or inject molding. When talking about other 3D printing technologies on the market instead, HP stands out in terms of durability, for example. With MJF, you can have part strength both on the XY surface and also almost as strong in the Z axis, which enables a lot of design possibilities that will not compromise the strength of the part. Talking about strength, parts are strong and can be tested in millions of cycles, and they are ready for production environments. Sustainability, not only in terms of material waste, which actually is a feature of additive in general, but specifically HP's material portfolio has a 70 to 90% rate of material recyclability. And finally, in terms of design freedom, without the need of support material, the possibility to print strong parts in every direction and creativity, there is also no limit to what Multijet Fusion can do. And that is because Multijet Fusion is a powder bed technology. So the powder bed acts as a support. To understand that better, let's have a look at this video. So HP Multijet Fusion is a powder bed technology, as I already said, which means that what happens is that we spread thin layers of powdered material, and then what happens is that some HP inkjet printheads apply liquid agents drop by drop across the bed. Then, when the temperature is raised up to the fusing temperature by infrared lamps that apply energy, only certain portions of the powder actually fuse to create the desired shape. And this whole time, sensors and thermal cameras monitor the temperatures to ensure that the process is operating as expected. And once finally a layer is complete, the platform lowers and the process repeats until the print job is complete. So the key of this process is in the liquid agents, the fusing agent, which attracts the heat, and the detailing agent, that is water-based, and instead deflects it, evaporating for the most parts in the process. It's very similar to 2D printing because it also leverages the same inkjet technology. Let's now move on to the next section of the presentation. How can additive manufacturing actually be applied to robotics and automation? Where is the advantage? Let's start by looking a little bit at the market. What are the mega trends that are impacting robotics and automation right now? Over the last several years, we've been seeing a number of them across the robotics and automation industry. For example, a huge growth in robotics as more and more companies look to automate their processes and minimize simple, repetitive manual tasks. All of this while also bridging labor gaps and reducing cost. With that growth, we're seeing more of a demand for not just the same and old solutions, but safer solutions, more sustainable options, and also more flexibility in production lines, the ability to deal with higher variation, smaller batches, faster changeover times. If we stop and think about all of these trends, we see that they all go hand in hand with the benefits AM can provide when used efficiently. So we can see that industry is catching on. And as a result, we are seeing rapid adoption of additive manufacturing for a wide range of industrial applications. For example, mechanical components such as electrical housings, bearing cages, gears, pulleys, or again, jigs and fixtures, so any inserts, any brackets, masks, etc. All of the air conditioning applications, Then pipes, tubes, and fluid systems, which also includes pumps and valves, turbines, irrigation systems. And finally, a topic that we are going to deep dive into today, which is Endofarm toolings. So end effectors, actuators, printer adapters, sensor housings. When you first think about 3D printing, it is pretty common to think of prototyping, and that is actually a great place to start. But in reality, the technology has advanced to a point where we can now print very robust, reliable end-use parts. But how do you get started with additive, especially if it is the first time that you approach the technology? So it is very relevant to look into this question. How do I start designing parts for additive manufacturing? And the answer in parts depends on where you are at in your design cycle. The earlier on, the easier it will be to take full advantage of the technology, and the bigger the benefits in terms of parts performance, in terms of cost and time to market. As you can see in this graph on the slide, moving back on the timeline that goes from defining a new product to actually introduce it in the market and provide service and support around it, the opportunity for additive manufacturing is bigger going backwards. So to analyze this, let's move from the latest stage of the development cycles to the first one, from end to start. And let's see what happens when introducing 3D printing in your facility. So we are here at the manufacturing analysis stage. And let's keep in mind that even if you have a part design that's fairly set and there isn't a lot of jiggle room for change, there still are a number of potential benefits in terms of time, weight, and cost savings. For example, if we are moving from a machined part to a 3D printed part, one option is to lightweight parts. With subtractive technologies, often the goal is to reduce operations to minimize part cost, but that also leads to the heaviest part. But with additive technologies, you want to minimize material used to both minimize cost and weight. All go hand in hand. And here are some ways that you could approach that. Hollowing the parts, creating honeycomb latticing structures, and that really depends on the part and on the structural integrity that is required, or you can try to optimize the topology of the part, finding the best distribution of material, obviously given an optimization goal and a set of constraints. Again, as I said before, this happens when you don't have a lot of wiggle room or you don't really have the experience to go through the process to ideate an intricate design that you could achieve from 3D. Let's look at an example, specifically an example of lightweighting. These large format printers that you can see in the photo use several machined aluminum and steel components. We started investigating on how to replace these components with 3D printed versions. And what you can see here is the design progression for one of these components. What started as a machined block has ended up as a topology optimized structure that obtained a 50% cost reduction, a 93% weight reduction, and not to mention the huge carbon footprint reduction in the production of this component. But while this is all very impressive, I really want to point out that you don't have to go all the way to this final iteration to unlock most of those benefits. Even by taking just that first step with the very minimal design changes, we realize a significant improvement. Even with very limited time or dedicated resources, you can achieve design improvements with additive. Let's go back to our graph now. And what happens if we start a bit earlier, when there is a little bit more flexibility in your design? Now you can start optimizing for the specific 3D printing process that you have selected and potentially consolidate multiple parts together in a more efficient form. Let's look at these other examples in terms of assembly consolidation. This is a drill extraction shoe used to remove silicone sludges and water that's used in our laser cutting process to make printhead nozzles. The original was made up of 7 parts, mostly machined. So you can immediately see the benefit in consolidating this assembly into just one part. It's not just easier to assemble, but it also eliminates all of these joints, reducing any risk of leakage. That is the #1 thing that you want to avoid when you are dealing with fluid systems that need to be air or fluid tight. To give you some numbers, the cost reduction obtained with this product was of 95% compared with the original part. The weight reduction was of approximately 90%, both due to topology optimization and material reduction. And then there was also a lead time reduction because CNC machining required 3 to 5 days of processing, while HP's Multijet Fusion completes the same task in 24 hours. Let's go back to our graph and let's analyze what happens in the best case scenario when you can start development with additive manufacturing right when you are designing your product. Because this is how you will really be able to find the best fit for the technology and take the most advantage of it. To do that, let's introduce it immediately with an example. To demonstrate this, I want to walk you through an example of what that design process could look like. So as the customers become more experts in the technology that they use, we start seeing parts that are directly and specifically designed for 3D, not adapted, but created starting from the manufacturing method. What you can see here is the design progression for this pneumatic gripper. In their first step, what this company did was test out the basic shape and effect of various air pressures on these spiral fingers. From there, they improved on the initial design in order to optimize the movement based on regulating the air input and frequency. Then they started integrating it into a consolidated gripper. And at that point, they found an issue with simultaneously lining up the finger movement. So they added this central mechanism that you can see in the last picture to line up that motion and also provide an end stop to the gripper opening movement. Each of these steps can take a matter of days, or even less if you print multiple design options at the same time. So you can go from a concept like they did of using mathematical growing functions to create a fast and accurate gripper to finally reaching the solution in the span of just a couple of weeks. Having talked about how additive works and how it can actually be beneficial to the world of robotics and automation, it is now relevant to showcase how some customers that we work with combine decades of manufacturing design expertise with 3D printing to integrate air channels, to integrate camera holders or sensor brackets into the Endofarm tooling themselves, to create multitask performing end effectors, reduce cable clustering around the robot arm, or reduce changeover line downtime. So let's have a look at a couple of customer success stories. And to start, I will play a video from an Endofarm tool manufactured by IAM 3D Up that will show you part of HP's 3D printing value proposition for robotics and automation. So as you saw from the video, this is an example that really highlights design freedom. IM 3D Hub's client, Continental Automotive Spain, is a tier 1 auto supplier who naturally uses a lot of robotic systems for handling the parts. Together, they designed this custom shape to fit the part it's picking up, which is also designed to minimize material used while still being very robust. Delivery time in this case is only 24 hours, and the Endofarm also has 4 integrated air channels to connect in 4 suction cups. All in all, they saw an 87% reduction in weight, which also enabled the customer to use more affordable robots with lower load capacity. Now that Continental understands how to leverage additive manufacturing, they are completely rethinking their approach to complex workflows. Also because automotive companies often deal with moving bulky parts very quickly and precisely, which technically leads to an increase of system complexity and cost. Plus, some of their final finishing and assembly operations are performed manually because of the level of complexity involved. Moving on to another application, I want to show you this Endofarm tool manufactured by Savage Automation. Savage Automation specializes in 3D printed Endofarm tools. And in this case, for this specific Endofarm, they worked with Additive America, and they produced this clean and compact design that also has integrated air channels. Specifically, this end effector uses 32 suction cups to pick up 16 components for a hand sanitizer packaging line. What they do is pick them up from an injection mold and place them on a conveyor, complemented by 8 pneumatic grippers that pick up the runner and place in the scrap bin. In this case, they managed to obtain a 60% weight reduction. The next example that I want to show you comes from FishSep S3. The original design for this assembly was machined, and it was almost 5 feet wide. That much weight put a lot of stress on the system, and it also limited the speed and precision that it could move at. So they started to look at redesigning this arm and quickly found that the parts were going to be too complex for machining or even inject molding. If they were to go to the route of inject molding, it would have required 11 different components in the mold, which would have been tremendously expensive, and they also would be locked into a design. So they ended up making this painting arm almost entirely out of 3D printed parts, resulting in a huge weight reduction and an 80% size reduction. Reducing weight unlocks a cascade of benefits because they were also able to reduce the size of motors and gearboxes used to move this tool around. Next example that I want to show you comes from one of our service bureaus, which is Whitehurst 360 Degrees. This application is a vacuum suction cup for the automation industry. Specifically, it is a nice example to showcase how creative you can get in terms of design freedom, because this robot arm is actually made of 2 different materials, PA11 and PA12 glass beads. This happened because the front part of the Endofarm needed to be more flexible, while instead the strength of the PA12 on the back part was necessary to create the vacuum Endofarm tooling that was previously manufactured in aluminum. By transitioning to 3D printing, Whitehurst 360 Degrees was actually able to reduce the cost and time to part by 50%, while also integrating air channels into the part, which eliminated the need for an assembly. But it's not all about Endofarm tools. As we saw in a previous slide, the applications of 3D printing in the automation space are several. One example from the jigs and fixtures world for collaborative robots or cobots is this protective skin made of TPU by Oshler. Thanks to the material's properties, such as its flexibility and the lattice structure it was manufactured in, this application acts as a collision buffer, absorbing hits in case they occur, so preserving the robot's structure and drastically lowering the risk of injuries. Other big advantages of this application are speed increase in the robot operations, since collision forces are highly damped, then also the fact that the system won't need any additional sensors, and finally, the way it acts as a permeable skin, preventing heat accumulation due to its open structure. And talking about TPU, let's address once more how important the material choice is when trying to manufacture the perfect application. Forerunner 3D is a service bureau with our technology, and they are using a TPU from Lubrizol to create a number of compelling applications. For example, the ones that you see on the slide. On the top, you can see the load-unload Endofarm tool, compact for easy manipulations by robots, and Class A safe. This means that it won't damage the delicate parts finishing while handling them. At the center of the slide on the left, you can see a nesting tool, which is actually paired with the Endofarm tool that I just described. It is obviously also safe for automotive Class A surfaces. The soft touch surface of the TPU will not damage the painted surfaces. On the right side of the slide, you can see custom suction cups, since this material can be airtight as well. And finally, at the bottom, you can use elastomers for gripper fingers or fixture pads, anywhere you might need some additional compliance. For the next application, I am going to play a video from one of our customers based in Italy, Campetella.
Fare automazione forse nel tempo è cambiato un pochettino, perché quando noi abbiamo iniziato ci si chiedeva di realizzare qualcosa che aiutasse l'operatore a lavorare meglio. Oggi fare automazione significa invece industrializzare dei processi con tempi sempre più brevi.
Campetella lavora oggi in 40 paesi nel mondo e produce all'anno circa 500 sistemi robotizzati che poi si dividono in varie industrie di riferimento, e quindi parliamo dei mercati del packaging, del farmaceutico, del medicale, piuttosto che nell'houseware o nell'automotive.
Noi per il tipo di lavoro che facciamo, quindi quello di inserire delle etichette nello stampo, siamo molto legati alla forma dello stampo. Quindi è una forma estremamente variabile. Con l'avvento della stampante 3D questa è stata un'agevolazione enorme, che ti apre un mondo che penso sia frenato solo dalla fantasia.
E la flessibilità fatta tecnologia è qualcosa che sicuramente ha cambiato il modo di concepire sistemi customizzati e ha cambiato i tempi con cui ragionare nuove prototipazioni e anche nuove commesse.
Ad oggi la maggior parte dei componenti che abbiamo implementato in stampa 3D nelle nostre isole sono quelli che vanno a caratterizzare il prodotto del cliente, quindi tutto quello che è un sistema di presa, un tampone, un porta etichette, quindi diciamo la parte di personalizzazione. L'utilizzo di parti stampate in 3D ci permette di avere sistemi di presa che hanno la stessa funzione se non migliore dei precedenti, e questo ci permette di avere macchine non solo più prestanti, ma di poter far ridurre i consumi delle macchine e di innescare qualcosa che fa sì che abbiamo tempi cicli migliori con macchine con consumi ridotti.
Con la stampa 3D abbiamo raggiunto degli obiettivi che credevamo irraggiungibili. Abbiamo per esempio nei tool per sistemi di etichettatura diminuito del 50% il peso dei mandrini che venivano precedentemente realizzati tramite tornitura. Il time to market degli stessi attrezzaggi è sceso da 8 a 4 settimane proprio grazie alla realizzazione molto rapida di questo tipo di componenti.
Essere affiancati comunque da HP è importante sia dal punto di vista del service sia dal punto di vista della sicurezza tecnologica, e in più l'assistenza. Avere comunque una casa così grande dietro fa sì che l'assistenza sia repentina e soprattutto funzionale.
Oggi fare una macchina speciale avvalendosi del 3D ci permette di fare una macchina che all'occhio sembra una macchina ingegnerizzata e già una macchina di mercato normale, mentre magari è il primo prototipo.
So in the video that we just played, you saw a series of robotic components for labeling machinery. Basically, with additive manufacturing, Campetella managed to join mass production and customization, creating ad hoc solutions for their needs and production line specification. Here is the part that we have here in our demo room. This cable holder, designed and manufactured by Wagtus 360 Degrees, can easily be attached to robots using a film hinge. This one is actually made of PA11. Leveraging the ductility properties of PA11 material and the design capabilities of HP Multijet Fusion, they were able to create a design that enables better cable management on the robot operating, enabling easier mounting and better robot arm movement. Going back to Endofarm tools instead, here I want to show you an application from Thinktech 3D. Thinktech 3D uses HP 3D printing solution for functional and unique end-of-arm tooling designs that are actually optimized for pick and place. So by leveraging the design freedom enabled by 3D printing, Thinktech 3D was able to integrate various functions into the end effector, such as integrated air channels, brackets for cameras, as well as cable management systems for more accurate movements of the robot arm. The next and last application that I want to show you comes from CNC Urfel, a company that specializes in manufacturing and process automation. One of their customers was looking for ways to make their production operations more time and cost efficient. And one of the parts that they identified as a great candidate for 3D printing was a multi-glipper assembly that you will see in this video.
Ich habe die Firma CNC Automation 2006 gegründet. Wir sind heute 18 Mitarbeiter und sind vorrangig tätig im Bereich der Maschinenautomation mit Robotertechnik. Den 3D-Druck nutzen wir seit gut einem Jahr. Die Möglichkeiten des 3D-Drucks sind nahezu unbegrenzt. Hier haben wir zum Beispiel einen Greiferaufbau, an dem wir dann auch diese verschiedenen Greiferfinger gedruckt haben. Hier sehen wir diesen Greiferadapter, der früher aus verschiedenen Bauteilen gefräst wurde, und obenrum zum Beispiel auch diese Greiferfinger. Bei der Herstellung mit dem Multijet Fusion haben wir deutlich kürzere Durchlaufzeiten als bisher, und die Qualität ist für unsere Anforderungen absolut perfekt. Die Bereiche, in denen diese Technologie zum Einsatz kommt, immer breiter gefächert wird und im Business wie im Konsumerbereich nahezu keine Grenzen mehr gibt. Der 3D-Druck wird mit Sicherheit in alle Bereiche der Industrie einen ganz großen Einzug halten noch und einiges revolutionieren.
We've come to the end of our presentation. So, in order to conclude, let's take a step back and let's actually understand which are the key takeaways from all of what we talked about today. 3D printing has a very specific value proposition for the robotics and automation industry. You can utilize design freedom enabled by HP's Multijet Fusion technology to actually streamline workflows and improve optimized performance without compromising part strength. Also, with HP's Multijet Fusion technology, Endofarm tools can be customized to meet end customer specific needs, enabling lower maintenance. These tools can be built to perform multiple operations with specific customized frame shapes to fit with the manipulated parts, requiring less adjustment compared to tools manufacturing with traditional manufacturing methods. Grippers, robotic end effectors, they can all be custom designed and built for your specific application, and you can also increase speed and accuracy. 3D printing with HP's Multijet Fusion technology can greatly reduce the lead time between the design of a component and the actual production of the real part. Within days, our customers can create physical representation of each product rendering, from conceptual models to functional prototypes, and put functional prototypes in the hands of their customers. Finally, additive manufacturing can help reduce costs through design, material, and simplification of production line. You can save on equipment, not only the molds, for example, but also all of the additional tools and equipment that are necessary along a traditional manufacturing line. And you can simplify these manufacturing lines by reducing the space required to operate. So that concludes my presentation. Thank you so much for your attention and for your interest in the benefits of additive manufacturing for the world of robotics and automation. We are now going to have a live session of Q&A. So feel free to submit all of your questions and your curiosity, and I will try to answer to them. Also, here on the screen, you will have my contact details, just in case you want to contact me in the next days or in the next weeks for any doubt that you might have. Once again, thanks for your attention and for listening.